My name is Beate Bender. I hold the chair for product development in engineering design at Ruhr-Universität in Bochum, that's in Germany. Obviously, as your session chair, I have already had a glance at the presentations prior to this session, and I can tell you we're looking forward to an interesting session on how to improve engineering design as well as engineering design processes. Since we will see now all the presentations in one row, you can use the chat function if you have questions while you're listening to them, but you can also ask live questions after the presentations. So now the stage. Now we're there. Now the stage is yours. Please mute your microphones. I will do that as well to look at the presentations. Thank you.
Thank you for your interest in our research on responsibility assignment in systems engineering. The complexity of systems to be developed continues to increase. Systems engineering is an approach which can help to overcome the challenges of high system complexity in the product development. Therefore, the International Council of Systems Engineering, INCOSE, defines processes of systems engineering with their inputs, outputs, controls, etc. The transfer of these theoretical approaches and the successful implementation of systems engineering in the company is challenging. One problem that we see again and again in our different projects with big German automotive companies is the lack of defined responsibilities. What we see so far is that in the literature and systems engineering handbooks, responsibilities are not clearly defined and specified. That brings us to our current research question: how can a generic assignment of responsibility in systems engineering be done based on the systems engineering artifacts? But before we start into our research, we have to clarify 3 words. First of all, systems engineering. Systems engineering is a structured cross-disciplinary approach to develop complex technical systems. And the overall target of systems engineering is to reach a cross-disciplinary optimum within a fixed time frame and budget. The second word is tailoring, and tailoring describes the configuration of the systems engineering approach to the project or company's specific conditions and needs. And the third word that we have to clarify is the role model. In systems engineering, we have the so-called systems engineer, and the systems engineer role is divided in a role model into different sub-roles. When we are talking about responsibility assignment, the RACI method is one of the most used methods in the industrial field. There are different variants of the RACI method, such as the RACI or the RASCI or the RASCI-VS, ratio or whatever. And when we are conducting this method, we are assigning the letters R, A, C, and I depending on different roles on different tasks. So the R is set for a responsible, A for accountable, C for consulted, or I for informed. Within our approach, we started in 3 steps. First of all, we identified a representative systems engineering role model on basis of a broad literature review. In a second step, we identified relevant systems engineering artifacts. Therefore, we did an analysis of the INCOSE handbook. And in a third step, we did a derivation of a generic responsibility assignment in a matrix based on a literature review and our industrial practice. The first systems engineering role model was published in 1996 by Shared. Since 2021, there are more than 1,000 of publications of role models. Gräßler and al. Analyzed different models on their fitting on the model-based systems engineering processes in a meta-study. And with multilinear scaling and clustering, they came up with 15 roles which are applicable for systems engineering. To identify all relevant systems engineering artifacts, we used the INCOSE handbook to collect all of the relevant IPO diagrams regarding to the systems engineering processes. Based on this, we extracted all the artifacts out of these IPO diagrams, and in a third step, we identified just the relevant artifacts out of these 367 artifacts in total. That means we got rid of duplications. In the third step of our research, the responsibility assignment is performed. And therefore, for each role, either a responsible, an accountable, and consulted or informed, or none of those is filled in the field using the letters R, C, A, and I. The evaluation of our research is done in two steps. In the first step, we've done a cluster analysis on our metrics. And in the second step, the results are reflected in an ongoing systems engineering transformation project. And what we see so far is that the first and the fourth cluster are the only clusters that contain of only one role, the technical manager and the project leader. And the second cluster contains of three roles, the systems architect, the implementation engineer, and the configuration manager. And the third cluster contains of all remaining roles. And what we can show here is that cluster 1 and cluster 2 are quite far away. And this is consistent with the actually tasks of the two roles, which are completely different. While the project leader is more into the organizational perspective, the technical manager represents more the technical view on the system. The remaining roles, as I said, are divided into two clusters. Cluster 2 contains all roles which are mostly consulted in the field of the architecture roles. So we could call it as the architecture team. And cluster 3 contains all remaining roles, and they represent the specialized roles in general. So on a practical level, you can say that small systems engineering teams in small companies should exist out of at least 4 persons, which will position the roles in the field of these 4 clusters. In our practical systems engineering transformation project, we conducted multiple workshops on responsibility assignment during that process. And what we can see there is that the results that we achieved in discussions with experts out of the company are quite similar, or are similar to the results of our current research. I thank you for your attention, and now I'm happy to answer your questions to our research.
Hello everyone, my name is Aleksandr. I'm from the University of Bradford, and I'm here with you today to present you a piece of work called Towards a Model-Based Systems Engineering Approach for Robotic Manufacturing Process Modeling with Automatic FMEA Generation. Here is the agenda for today's presentation. And first, I'm going to start with an introduction, providing discussion on what actually FMEA is and what are the issues associated with traditional FMEA generation methods, also providing goals for the current work. Then I'm going to give discussion on the top-down robotic manufacturing process decomposition, present you with the generic methodology towards the automatic PFMEA. This is followed by the MBSE robotic manufacturing process model database structure, basically showing the actual structure of the model, which we have, and finishing with the MBSE output information flow into PFMEA. So let's start with the introduction. Failure modes and effects analysis, in short FMEA, is a well-known method to support systematic analysis of a product or process to identify potential failure modes and plan for robustness measures, including robust control plans for a manufacturing process at the design stage. However, with the traditional FMEA methods, there are several issues associated with them. They're labor-intensive, they're often unstructured, they are time-consuming, they are subjected to errors, and they're difficult to keep up to date and interpret. As a result of this, FMEAs are often regarded as deliverable to the customer rather than a tool that can be used by engineers to influence design decisions. The underlying idea of this work was to actually address all of these issues and propose model-based system engineering assisted automatic FMEA generation methodology. As a result of this, two main aims were defined for this project. So first of all, it's the development of the MBSE framework for top-down systems engineering approach to robotic manufacturing process design, modeling, and analysis. And second is the automatic generation of the PFMEA from the developed model. MBSE framework development was supported by a case study, which was a robotic manufacturing process. However, prior to MBSE model building, it was important to establish process decomposition technique. For this purpose, top-down approach was selected, and it involved three key levels. The top level being the process level, which essentially involved the process itself. The next level being the operational level, which involved all the general operations of the manufacturing process, and the sub-operations they split into. And the machinery level, which was the deepest level, and involved the operations at the actual machines. It is important to note that for each of the process flow steps, critical characteristics were assigned. This way, a cascade of critical characteristics is formed when all the three levels are combined. Once all the levels are established, it is possible to generate MBSE models around them. And despite the fact that database structure for the MBSE model is going to be discussed in the next slide, it is necessary to give a brief introduction on how it is formed in order to understand the concept. So MBSE model is an input gets a lot of information from the domain expert knowledge, which comes in the form of SIPOC mostly. So SIPOC is the abbreviation for the suppliers, inputs, process, outputs, and customers. And essentially is a tool, well, spreadsheet, which possesses all the relevant information regarding the process steps involved from the beginning to the end. This includes all the characteristics and specifications. So SIPOC allows us to establish the process flow information within the model. And in addition to that, domain expert knowledge is also used to define something that we call the ontology dictionary. The ontology dictionary is essentially a database for the elemental operations regarding the possible failures that can occur with these operations. So this way we can define the failure modes. Now, in order to implement the automation, the concept of the failure chain has been employed, which was presented by the AIAG VDA. And the failure chain concept essentially shows the link between the failure mode, the failure cause, and the failure effect. So if we implement this concept across the multiple levels which we have, we can establish the link between the failure modes and the failure cause on different levels. And then by the application of the scripts, we can generate the, and assembling all the information, we can generate the PFMA at each of the levels. In addition to that, we can generate the fault trees, and as we go down through the levels, we can propagate the fault tree, expanded further down. MBSE model database structure is composed of the four main fields, that being the engineering knowledge, involving SIPOC and ontology dictionary, process architecture, which includes the process step information within the model, characteristics, which is the part in, part out process characteristics, and characteristics and correlation matrix, and failure modes analysis, which includes the information about the failure mode, fault structure, fault tree, and failure effects. Due to the time limitations, I cannot go through the deep explanation of how everything is formed. Please refer to our publication for more information on that. However, this slide shows simplified information flow through the MBSE model and the output into the PFMEA. So we start up with the SIPOC, we extract process architecture information from it, and out of which we can straight away generate process functions requirements column within the PFMEA. Also, we process the information from the process architecture to the ontology dictionary and generate the failure modes and causes information, which feed the potential failure mode and potential cause counts in the FMEA as well. Also, from SciPack, we extract the characteristics, process them to the CC matrix, generate the failure effects, and fill the potential effects of failure count within the FMEA as well. Thank you very much for your attention. Please have your questions ready. We will be glad to answer them.
Hello, my name is Gavin from Linköping University. Today I'll present a paper that I've written together with Tom Sakao and also Johannes Maciejewski. The focus of this paper is on product service systems, which include combinations of products and services that are designed from a systems perspective while considering their mutual dependencies and interactions throughout the life cycle. The product service system can have different kinds of elements like products, software, and human-based service activities. From a design perspective, the potential time windows to design such different elements varies a lot, as you can see on the screen. Products and softwares before the start of the use phase can be designed and produced, while services can only be designed. After the start of the use phase, products can only be used. They can no longer be designed. The product design will be frozen. However, softwares can be redesigned and also produced even during the use phase in the form of software updates. For simplicity purposes, let's look at the differences between product and services only. Due to the inseparability principle of services, services can still be designed during the use phase, as when they are being deployed, they are simultaneously produced and used. This offers service designers a greater degree of flexibility after the start of the use phase and also before the start of the use phase. They can assign values to service design objects throughout the life cycle, providing product service system designers a greater competitive advantage when compared with typical product designers. In practice, we have observed that even though PSS providers have this competitive advantage over product developers, that advantage is often not optimally used. Before the start of the use phase of products, product and service designers tend not to interact with each other and not consider the mutual interdependencies of the products and services being developed. Rather, they operate in silos. After the start of the use phase, the product design department is frozen, and although the service design department can still design the services, their ability to do so tend to be restricted. This is due to the potential mutual dependencies of products and services. Even though there is a higher flexibility on the temporal dimension for service design, it is often not optimally used in practice. Either too many or even too few decisions are made for the service design at the end of product design. We refer to this phenomenon as falling into the service design trap. In order to help designers avoid falling into the service design trap, we have developed a product service dependency matrix. This matrix is the result of a knowledge base that we have developed through a scientific review of multiple journal papers, where we were able to document around 42 cases of product service dependencies or integration across multiple industrial sectors. Through the review, we were able to abstract 5 product design parameter classes and also 7 service design parameter classes. We were also able to abstract 3 archetypes of dependencies between these product and service design parameter classes. CP refers to service being unilaterally dependent on product element. PUS is vice versa, while PBS refers to bidirectional dependencies between the product and service DP class. Shaded cell indicates that there is no dependency that we could find in those 42 cases. To elaborate, I can give you an example. Here we can see that capability or service capability is unilaterally dependent on information transferability of a product. We found in multiple cases that by installing certain sensors and IoT devices, the products could transfer information regarding the overall product systems from the use phase to service technicians who could effectively design their predictive maintenance. Therefore, here there is an SUP dependency between service capability and information transferability. This knowledge base and the concept of service design trap was validated by applying it to a real case with the company Alpha. Managers from product design, service design, and sales were involved, and these managers reflected that several of the dependencies identified in the knowledge base are relevant for their own product service system. Although several of them were already exploited by the managers and designers, some were considered to be more worthy of a thorough investigation. They also reflected that there were multiple occasions where they had fallen into the service design trap, where the service staff had to cut through a huge complex product in order to access a critical component deep within the product, so that they could carry out the service that had been promised. The concept of the service design trap and also the knowledge base was useful for them to identify and prioritize important dependencies, and also useful to provide pedagogy to less experienced designers. Currently, a formal way of taking account of such issues was missing in their existing design process. To summarize the key contributions of this paper, we have provided a new rationale for why PSS design in practice often does not exploit its full potential, mainly based on a theory of inseparability of production and use of services. We have also proposed a high-level representation of dependencies between product and service design parameters in the form of the potential dependency knowledge base. We have also shown reusability of the knowledge captured across multiple product service integration cases from different sectors by applying it to a real case of PSS design at a complex product manufacturer. We have recently published a journal paper that shows the application of this knowledge base to a different case of PSS design, again at a different complex product manufacturer. In order to access the latest version of the knowledge base, please visit this paper. Thank you for your attention.
Welcome to my presentation, Fault-Tolerant Function Development for Mechatronic Systems. My name is Ralf Stetter and I'm from the Ravensburg-Weingart University in the very south of Germany, and my co-author is Auto Pulm from the Hamburg University of Applied Sciences in the very north of Germany. So fault-tolerant design is here shown in a model which uses the level of concretization of the product models. So very concrete would be geometry and material. That's like the CAD description. And if you want to use fault tolerance there, it's possible to optimize sensor and actuator placement, to introduce redundancy, for example, like twin engines in a plane, over-actuation, overlap, and there are also possibilities for inherently fault-tolerant configurations. Bit more abstract is the physical structure, and here optimized physical behavior and effects are possible, also physical diversity, for example in sensing, and increased independence is possible. On the very abstract level are the requirements, and here for fault tolerance, the definition of fault tolerance specification and the exploration of possible faults and their consequences are the main elements. In this talk, we're going to concentrate on the functional level. On the functional level, if we want to have a design which is tolerant to faults, which can accommodate faults, which are not which are inevitable in complex systems, then it's helpful to have a transparent functional architecture, to use functional diversity, functional redundancy, and domain-spanning functional solutions. So if we now look at the function development in industrial companies, here I'm oriented on the V model, but I would like to point out a few points. So for example, usually in a company, you would start with customer needs and a business case. Then there is a system engineering layer which controls all the processes. Then there is modeling, simulation, and optimization as usual. Then there is a function called product management, which is present in most producing companies. And here is some system design, and the system design is also the function development, which is the main topic I'm going to talk about today. So this is function development, but if we look into functions, it's firstly important to look where do faults come from. And if you look at faults, usually there are no simple faults in industry because you work with experienced designers. However, there are certain faults which appear, and here we have generated a list which helps to identify the causes. So usually there are things which, for example, come from an unfavorable interplay of parameter values and product topology. So things which interact, which are not initially visible. So even experienced designers may have problems with these things, and that's why faults are emerged. Or for example, you have some unexpected side effects because you have some unusual product configuration. Things are brought together which are usually not brought together. Or you have some unusual operation profiles, so people operate in ways different than initially expected. Other points could be, for example, mechanical difficulties. So there could be some production tolerances which build up, or especially if they have some tolerance chains, or non-linear effects in parts, for example, stick slip. So these are things, even if you have experienced designer in industry, faults may emerge because of the things, and there are more given in the paper. So how do we have countermeasures for faults? And here on a functional level, which is very useful, is coming from TRIS or TIPS, the theory of inventive problem solving. And there is a relation-oriented function model, which uses usual functions and harmful functions and difference connections. So for example, we had an example where the fault was electromagnetic irradiation, which can cause inclination angle disturbance. So the product example was here a balanced two-wheel scooter, and therefore, because of this electromagnetic irradiation, we could have a disturbance of the inclination angle. And then these both are harmful functions, and a useful function was introduced to eliminate, that was to shield the electronics. So this is a fault accommodation solution, and especially this kind of function model is very helpful to clarify these countermeasures for faults, which are very often needed. So accommodation of faults can be investigated very good in this possibility. So let me come to this product development example. So one was the balanced scooter, which was developed at our university. So a potential fault, as said again, was inclination angle disturbance. So, and what are the functional accommodation components? It was not to make a better angle sensor, but we found that the most important thing was shielding the electronic and accelerometers. Here it's done by 3D print and the aluminum adhesive tape. And also we found out that another way is also in a different functional area that was in the electrical system, in the software. Even in the software, we could do this by applying appropriate filters. Another product development example is a motorbike engine, as you can see it here. So an internal combustion engine, which these days can only function together with the electronic control unit. Potential faults here were emissions which are higher than allowed, and also self-acceleration. And the functional accommodation components were many. So it was a complex thing which included many things: redundancy in function, function modeling of the physical system within the control system to have a better model-based control, and also limitation and calculation in various disciplines which were carried out to make sure that as both faults cannot appear anymore. Also, self-diagnosis was an important part, so that the system is always looking for its own emissions, and also for the self-acceleration, there was a testing on various levels that has to take place. Thank you very much for your attention.
Hello everyone, my name is Benedikt and I'm a PhD student with the Institute for Manufacturing and the Engineering Design Center at the University of Cambridge. On behalf of my co-authors, Carl Magnus von Beer, Carol Brain, and John Clarkson, I'm very happy to present to you our paper towards a contemporary design framework for systems of systems resilience. Let me start by giving you a quick overview of the background and the motivation of this paper. The recent COVID pandemic and the climate emergency have raised the need for resilient systems. Right at the beginning of the pandemic, my co-author Carl Magnus von Beer and I were part of a project at an NHS Foundation Trust where we could observe the organizational response of a complex adaptive system such as a hospital to the COVID crisis. Around this time, we started to think about resilience as a concept that is believed to support systems in anticipating and mitigating forthcoming uncertainties. Yet, the concept has become an umbrella term for many different conceptualizations. We later got involved in the work of the Reform for Resilience Policy Commission, for which we conducted a reflective analysis on the literature, key terminology, and issues of the resilience concept. With our resulting paper, we generally pursued 4 key objectives. We would like to discuss a consensus definition of resilience and make an attempt to define related terminology, to present resilience as a dynamic design process, to align existing ideas on resilience in complex systems of systems for an enhanced use in practice, and we do this by distinguishing resilience-enhancing properties, mechanisms, and activities, and finally, to apply the framework to the case study of hospital oxygen systems to showcase its usability. When approaching resilience theory, a good way to start is to ask 4 related questions. Resilience to what? Resilience of what? Resilience for what? And resilience through what? In our paper, we present a framework in which we want to contribute in particular to the 2nd and 4th question. We made several observations that have implications for today's systems resilience and that we try to capture with our framework. Let me quickly guide you through the most important ones. First of all, today's systems are highly interconnected and interdependent. For example, the COVID pandemic did not only present a severe risk to healthcare systems and the well-being of people, but also economic and political systems. Therefore, a systems of systems approach to resilience offers ways to conceptualize complex systems that are characterized by alternating states, subsystems, and nonlinear transitions. Second, these systems of systems that I just mentioned do not only need to cope with singular shocks, but there exists a wide range of possible change patterns and disruptions that can entail positive and negative consequences alike. Also, systems of systems are never fully complete and behave evolutionary. Hence, we decouple resilience as a primary system property and rather define it as a design process. Finally, recent crises have shown that similar systems can differ significantly in their ability to cope with disruptions. Also, the ways in which such resilience is achieved depends on the system and its particular environment. From this observation, we learned that for resilience, there's no one-size-fits-all solution. Instead, the local context is crucial. This highlights the importance of a definition and framework that can be flexibly tailored to the system or systems of interest. As a result of these observations, we base our framework on resilience on the following definition. Resilience is the process by which systems can face change and challenges in such a way that they evolve and innovate to drive and maintain socially agreed positive outcomes. As you may notice, we present the definition as a natural language pattern so that it can be easily changed according to the system of interest, but still provides answers to the first 3 questions on resilience: to what, of what, and for what. Now, the fourth question, resilience through what, is addressed by the framework we are suggesting, and I will describe its components one after the other. The center of the framework is the systems of interest. In our case, we distinguish 4 domains, namely the economic, health, environmental, and the community domains. As there are fundamental links between these domains that exert influences on each other, we also introduce their respective interfaces as separate individual domains. These interfaces cause minor or major ripple effects in the event of a stressor or change. We then argue that the vast number of concepts on how resilience can be achieved in systems boils down to 3 key dimensions, namely systems properties, mechanisms, and activities. These are often separately discussed in the literature and in practice, yet in our framework, we present them as layers around the system center. First, resilience properties such as flexibility, robustness, adaptability, and agility describe the behavior that can enhance the resilience of systems over time. Second, we distinguish mechanisms by which the system addresses a particular stressor or some sort of change. Ultimately, it matters how the resilience principles and mechanisms are realized or designed into the system. Hence, the final layer links the previous 2 to suitable activities. Taken together, we consider the orchestration or mapping of these principles, mechanisms, and activities as the design process of resilience. The key takeaway of this framework is that systems of systems that shall be better able to cope with different types of stressors need to continuously compose a portfolio of complementary resilience properties, mechanisms, and activities to preserve their qualities. This already brings me to the end of my presentation. I am very much looking forward to any questions or feedback that you may have. Thank you very much.
Thank you very much for these interesting presentations. And I think these presentations were well chosen because they all match or kind of they have interactions between each other. I still would like to start with number 1, and I will try to make sure that in the end we can discuss the overall implications. Paper 1, what I gather from the type of questions that the basic issue was that how does the literature review relate to practical application? So if you look at the questions, can the role models be defined in general, considering a context-specific design process, or what clusters and form would you have liked, or interesting clustering? Does it give an insight into how data and information in the stakeholders may interact on a project? Maybe we just start at the top.
Yeah, sure.
Can the role models be defined in general?
Yeah, thank you. Yeah, I can say that the role models that we figured out in the literature can used in different industries, but in our practical experience, it is specific used in the automotive industry. And what you have to say that for each industry area, you have to tailor those role models to the specific context. So right now, in our project where we are in a working with an international automotive company, one of our tasks is to tailor a generic role model on the needs of the specific company.
But this is something you need to do, and they can't do by themselves. So to be able to use your methodology, you require some sort of external guidance.
Yes, and yeah, you can say it like this. So right now we are supporting them, but in the end, the company itself, the people inside the company, they have to identify from their needs what kind of roles do they need, additional to the generic role model. So the generic role model, I would say, is a good framework that you can use for a company. But on top of it, you have to identify what kind of specific needs do your company have, And our task is to support them to find, to identify their own needs and to come to the role model that fits best on the company.
Thank you. The next questions refer to your clustering. Maybe James Gopsil might want to formulate his question. Or should I just read it from the chat? I obviously have to read it from the chat.
Yes, I can read. Actually, I don't quite get the second part of his question. So what clusters and forms would you like?
Maybe we start with number one. Does this give an insight on how data and information and the stakeholders may interact on a project? So do the roles actually refer to the kind of information and data that need to be exchanged?
Yeah. Right now, from our current research, we don't get any insights into that, I have to say, but it might be an interesting topic to continue our research in that field.
So we've got one additional question. Is there any overlapping between the activities that are performed by these roles? If yes, how would these clusters look like?
Yeah. Therefore, I have to say first that we did not had a look at the activities, especially which are defined in the INCOSE handbook. We just had a look at the artifacts, which are actually the outputs of the activities. But yeah, in general, you can say there is a relation, of course. Right now there is of course an overlapping of the activities or the artifacts, and that's why we came to these clusters. I think it's so I would say yes, there is an overlapping, and that's why the clusters are looking like that. Yes.
Okay, thank you. Any more questions to presentation number one?
Maybe I would come to the question from Ralf Stetter.
Yeah, that'd be great.
Yeah, this is actually a very interesting question. But I have to say no, we did not distinguish between the importance of the artifacts. But I think this can be a very interesting task. Or interesting view our second research that we can continue. But yeah, of course, therefore we first need to prioritize the artifacts. Yeah, that's nothing what we've done so far, but yeah, I will keep it on my scope.
Yeah, I agree. It would be a good thing, because from my experience in industry, there are some artifacts which are really crucial, and others you just need because they are somehow needed. And so I think it would enhance this if you could differ there.
Yeah, thanks a lot. Therefore.
You're welcome.
Okay, I would like to move on to presentation number 2. So that's Alex, right?
Yeah. Right. So the first
questions basically relate to the practical implications of your ideas. Maybe you can comment on that.
The practical implementation. So everything is established within MATLAB System Composer environment. So the processing codes are within MATLAB, and it's essentially, so the way we design it right now already, we've created also a set of little templates which user would need to fill in, and then the whole process of the generation from the start to the beginning, from the start to the end, including the model and the generation of the PFMA, would probably take about 3-4 minutes. So it's not one click; it's about 5 clicks. So yeah. So you can ask the questions entirely.
Okay, the question is, can you give an example for a critical characteristic?
Yes, first of all, would like to say that the critical characteristics at the very top level are linked to the design level. So design team would supply our model with the important bits which need to be looked after. And as an example, for example, this would be, let's say, a press force to achieve a certain sort of set press distance. So press force would be a critical characteristic, or tightening torque, or, for example, this can be also related to some safety concerns or governmental or environmental concerns. So it's it's meant to discuss the process clearly enough. Yeah, the system clearly enough. Sorry.
Okay, thanks.
Is there any criteria for generating fault trees from FMEAs? That would be my question too. Can you, like, how much can you change the subject you're looking at and still automatically generate your fault tree?
So in terms of the fault tree generation, well, essentially we take the approach that we cascade all the faults throughout the design process. So at the moment, there is no possibility to generate any specific branch. Although once the entire fault tree is generated, you can technically just hide the rest of the bits which you don't want, and it will trace you how that particular branch propagates through the fault. So that's a possibility.
I think just to add something to this, because this is linked with your question, which is whether the process models are created retrospectively or in parallel with the design process. So at the minute, we're very much working on designing a robo factory for an electric drive unit. So the system is the manufacturing is not there. We're working in designing, and therefore you cascade from the system level down to through the design, all the way through operations, and ending up with the design of the tooling, because this will all be fully robotic manufacturing in the end. So the point of the fault trees is really trying to develop them based on function failure modes, starting from the requirements of the part and all the other sort of, let's say, environmental requirements, including health and safety and so on, and productivity requirements, and ending up with faults or failure mechanisms at the tooling level. So it's very much a cascade. It's not a fault tree as people would normally consider a fault tree, but it's a tree structure of the propagation of faults. So in a way, it's very much related to what Ralph talked in his approach. Is just that we're looking at the fault propagation in relation to the functional decomposition through the system layers.
But still, the functional decomposition of the layers, isn't that related to the specific product? I mean, it's not a general property. It's something that is adapted for each and every product. So the fault tree must be adapted too.
Indeed. So basically, the way you're doing, as you do design in the layers, you would have multiple concepts, and then once you've designed, you come and refine your model. And that's really the logic onto which this works. So there is a process where you go through the design, you refine your model based on the design choices that you have made, and then basically the model is updated, and then the FMEA is updated. So and that's automatic. And one of the important concepts here is that we're looking at not allowing the engineers to go and modify an FMEA. You have to change the model in order to update your design risk assessment.
Connected to what you're saying, there was an interesting question rather at the end of the chat. Is there a risk in automatically creating this fault tree? Because in case it is wrong, you're in trouble.
Yeah, I think the point here is the reason we've taken this task is just as the challenges were outlined. So basically, there is a problem with the way design assurance and process assurance is currently completed, and that is that people don't actually like to do the FMEAs and so on. So we're not actually looking at replacing the designers by automating this process. Is really providing providing that augmented intelligence. So we generate some documents automatically, which are then going to the experts to consider and review. And I'm just going again with that important point that if an engineer, if an expert identified that something is not right in the document that they check, they need to go and check and change the model. Okay, because if you follow the process, the model should capture all the interactions, should capture all the faults and the propagation of faults through the model, and therefore if something is not right in the resulting documents, that means that some of the interfaces have not been appropriately captured or characterized.
Yes,
So,
but how would you know that?
well,
How can you know that your model is correct?
So there are two ways in which you can do that. One is you give it to the experts to review it. The other is to go and link it and simulate the model. And doing it in an environment like MATLAB System Composer with Simulink, you can actually you have the MBSE, you build a simulation model, and then you can start to simulate through controlled experiments all the fault scenarios. Well, I mean, people talk about.
So you obviously need some sort of validation for your model.
Correct. Yes. So, yeah. So basically, okay, you simulate and you do two things at the same time. You verify your model, but you also validate the integrity of the design.
Are there any more comments or questions to Alex? Okay. We move on to Abi then. That was number 3.
Yes.
And maybe I can start off with my question. My question was, you established this matrix, and I wondered, does that apply to any kind of product, or to every product, or to just the ones that you looked at?
Thank you for the question, Beate. Currently, the matrix is powered by a knowledge base that was built upon cases of complex products like turbines and
Is a
investment
smartphone a
machinery
complex
and
product?
similar.
Is it a smartphone?
Sorry?
I just
No,
wondered where do you draw the line from complex to non-complex products?
Yeah. Here it refers to industrial machinery mainly, mainly on the business-to-business context, and not on the business-to-consumer context. So smartphone would be ruled out in this particular context. But definitely, there could be dependencies that are similar in the cases that we documented, and also in the context of business-to-consumer area as well. So it is possible, but we haven't really looked into that.
And Ralph asked the question, how do you actually avoid the service design trap now with your approach?
Yeah, exactly.
Apart from the fact that you make it transparent, you show the interrelations, but there's nothing no measures or anything you suggest.
Yeah, the idea behind the matrix is to help designers narrow down the potential dependencies that have been observed in other cases. So they basically get support to narrow down the design space. The contrast, like without having such a support, they will have to look at the interdependencies between multitude of product and service design parameters. But what this does is it shows some common parameters that have been observed in different sectors to have dependencies between them. In a similar way done by TRIS as well, which abstracts patterns from a multitude of different cases and patents, and it shows which ones could be relevant and which could be applied. So that the designers during the early stages of design, they refer to the knowledge base, the matrix, and also use the tool in order to see if those identified patterns are transferable to their own cases. And by doing that, they investigate what kind of design changes they have to make in order to accommodate the interdependencies between the two. Does that answer your question?
Ralf, does that answer your question?
Yes, yeah, I think.
Okay.
Thank you.
Are there any other questions for Abi? Okay, thank you. We move on to presentation number 4.
Yeah, I think the first question is, what is the link between uncertainty and fault? I think that's a really good question. I think there is a strong link, and we can have uncertainties on the one hand in measurements, but also we can have uncertainties in design decisions. And both these things can lead to faults. So I think there is a link. Uncertainty is a bit a concept which can lead to faults, and then again it's interesting then to have systems which are fault tolerant or even resilient. Okay.
Does that answer the question? Obviously it does. And also I would like to ask the same question as I asked Abi. What exactly is it you're supposed to do? Because what I saw is that you show potential uncertainties or potential failures by experienced that can even slip experienced designers' minds. But what is it, a checklist you suggest?
I mean, it is a checklist. It's a checklist with things that should be checked. And it's also in the paper, there are also some concrete measures what you can do. So both think, look with the checklist for faults. And the other thing is, what could you do then to accommodate these faults? What's very important in your question is, it happens on each level. So you have this during a design process. So it has to be included in design reviews, because it's not something you do once in a product development, but you have to do it again and again at different stages. You have to do it at an early stage when you work with requirements and functions, but also in later stages and in later phases, even close to production ramp-up.
But don't you see the risk that the more checklists you have, the longer these design reviews get? Because what happens in the end, you have 5 million checklists for different aspects that need to be identified. Is there a chance you can actually integrate it in the process?
I mean, I think we have to. It's just because fault tolerance is mandatory. Today's complex products, you can't do it anymore. I think I also say we should have it nice and crisp. So this checklist have to be short, but it's a point. If you have this problem that your system is not fault tolerant and you detect it too late, then the rule of 10 applies. So obviously, we also have to think how many things can we consider, but the more we consider early, the better the systems get.
Okay, thank you. Are there any more questions for Ralf?
I mean, I think there was one question by Unal. I think this applicability of the design to autonomous vehicles, if we can think in this way also for software certification. I think that's also a very important question, because we will have this. We will have software certification. We will have system certification for autonomous vehicles. And there are already things existing like automotive spies, which will help us to clarify the processes. But I think it's an interesting development area if we look also at technological reviews. How do we assume that because autonomous systems, they can be dangerous? They need to be fault tolerant. They need to be resilient. And how can we assess this already during the development? I think that's an extremely good question.
Okay, thank you. So are there more questions for Ralf? Okay, we move on to Kaya, and I believe that we have one person trying to ask you a live question, because it's Kabir, pronounced correctly, I hope, who has a question for you. Can you probably explain your question, please? We don't hear you.
Can you hear me now?
Yes, thank you.
Yeah, sorry. Which presenter are you referring to? Sorry. To Ralph.
So presenter 5.
Presenter
to
5.
Kaya about
Kaya.
the concept of resilience. You asked the question.
Yeah, so interesting presentation, Kaya. The Michael question was, resilience is not a new concept. It's been here for a long time, isn't it? We just got more aware of it because of COVID and things. So what do you think what we have learned from COVID, a specific event, so that we learn new thing, or what we have learned so that we need to design the systems differently to before COVID or something. So is there any new insight we have learned, or any new properties, or so what is it?
Yeah, that's an interesting question. Thank you very much for that. So I think, yes, you're very right that resilience has been discussed in various academic fields for a long time already. I think what COVID has changed is that we really have this understanding of that this is a concept that is not only located in one academic area, but addresses essentially every system that affects our everyday life. And it has not only made everyone aware of the concept, but also about the gaps that are still existent there. So what does resilience entails in specifically, and how it can actually be achieved in systems, which is a very unclear questions at the moment. And well, this backs the question of what are the processes and the methods we need to use to navigate the field of resilience and the already known concepts. How can we tie them together and to learn from that? And just to add up on that, I think it was not only COVID, but also every the events that happened either during COVID or what is the current situation. So for example, also the case of the Suez Channel, the incident there, or the current Ukraine crisis. I think this has really changed the dynamics of resilience, not to be focused on a single event, which can have negative consequences, but to really appreciate the overlapping nature of different events that may have good outcomes for systems and very bad ones. And the aim of the resilience concept is really to say we want to extract the good ones only, but we also want to avoid or be better able to cope with the negative ones. And I think this awareness and this the search for ways to conceptualize this and to operationalize this for systems, I think this is new. Does this answer your question?
Yeah, thank you. Yeah, it does. It just last question is, do you think the resilience can be the definition of resilience? The term could be different for different system, or one definition fits? I know you have 3 elements on your definition, but do you think to be more specific, make it operationalize, we need to think differently for different systems, size of the systems, organization, and things?
I do think so, and I think this question also, I mean, this is you're asking something that is reflected in other questions that have been asked, like what does anti-fragility mean? What is the interplay of risk and resilience? So I think this whole field suffers a little bit from that these definitions and what they entail are not. That there's not enough clarity in those concepts, and this is why it's so important for this framework to be flexible, to these different perspectives, right? We distinguish the 4 properties: adaptability, agility, flexibility, robustness, and they in itself can mean different things for different systems. So it's really important also to coming back to your, I'm not sure who asked the question about the perception. Felician, you asked that one, to find methods to capture the different perceptions, because only that will make the process of resilience meaningful, right? To have the different perspectives of stakeholders involved, and then to decide what are the different combinations of mechanisms, properties, and activities to make a resilient system. So yeah, some systems just need to be designed very, very robust, and some need to be designed very, very flexible, and to find out what are the links here. And this really depends on how we define the system in itself. And this is why we've provided such a flexible definition pattern.
Thank you.
Then we come back to the question how to validate your framework. This is James asked that. So how do you know you didn't miss out on anything really important?
Yeah, that's an important one. So what we've presented in the paper is an initial case study that for the project we've been involved with the project that has sort of kickstarted this project. It's been on oxygen systems as a technical system within a broader hospital context. And what we've tried to do is to identify what were the elements that have contributed to resilience in that specific systems, and how do they relate to the framework we propose, and what are the learnings from that. And we intend to do that for different other systems. There's already some work underway in terms of automotive product recalls, and also humanitarian aid in the Gaza Strip, to see how does resilience play out in these cases? What are the elements, and do they actually fit our framework, or is something missing? So this is the current approach we're taking here.
So we can probably move straight on to Peter, who expanded his question meanwhile on where do you draw the line between resilience and anti-fragility, because this comes back to validation too, because you need to know what it actually is you're trying to validate. Maybe yes, Peter can elaborate a little on his question, or you try to answer first and we hear if Peter is happy with that. Okay, go ahead. He doesn't say anything.
Okay, yeah, I'm sorry, I'm in the process of reading the question. So it's a line between anti-fragility, evolution, innovation seems to associate these qualities more with anti-fragility, while resilience is more concerned with coming back to the initial state. So I mean, this is essentially what we're not proposing, that resilience is not coming back to the initial state, but a sort of iterative process, because it's not only about the events that we are facing in the next week to 2 weeks, or not even in the next like 5 to 10 years, but what is really on the horizon, and how can the system iteratively evaluate or build the resilience in itself. So this is and in an anti-fragile. So I actually think that fragility is not can actually be helpful for resilience, to make a provocative statement here, in the sense that if we have, for example, new technology coming up, then and there are very good, socially agreeable, good outcomes from such a technology, then why? And then I think it would be even helpful for a system to be fragile, to be to be resilient in the overall context, to really capitalize on the upcoming technology.
So are you proposing a different definition?
I'm proposing a different definition for resilience as a process, yes.
Maybe we can look at what, Felician? How do you pronounce that?
Felician Campean, yes.
Felician.
Yeah, I think
because what you said, what you brought up is that isn't learning a quality that every resilient system needs. Is that the case, Kaya?
I think learning is a very important attribute of a resilient system because it enables us to well, capitalize on what has happened in the past to the forthcoming uncertainties. What is, I mean, hopefully happening at the moment, but at the same time, what we see is that not every situation is different, and also the next pandemic will be different. So yes, there is a learning aspect to it, but there's also other attributes that will enable systems to be resilient in the future. For example, also the sharing of knowledge from different systems, or to be flexible to new situations. This is not only based on the learning from past experiences, but also something that needs to happen ad hoc.
Okay, thank you. Are there any more comments or questions? I start getting confused with the chat now because there are several issues discussed in parallel. Okay, so from my point of view, the conclusion of today's presentations was that as soon as we start developing methods to support designers, these need to be integrated into the design process, and they need to be validated. And in case they relate to risk or resilience, we need to know what it actually is we're trying to support with our methods. Is there any open question, any open final question or comment from anyone? Okay, then I thank everyone, specifically the design helper Marco, who facilitated all the technical problems. No, you didn't facilitate the problems, you facilitated the solutions. I thank all the presenters and I thank the audience for your lively discussion. Hope to see you soon, and bye-bye.
Okay,
Thank you.
Thank you very
Bye-bye.
much.
Thank you. Bye.
Thank you. Goodbye.